I welcome you all for this lecture 2 on unit number 5 for the gas turbines. In the lecture 1, we have discussed about the working principle of a simple gas turbine power plant. We have also looked into the open cycle and closed cycle gas turbine power plants, the Breton cycle, thermodynamic cycle used for operation of gas turbine power plants. And additionally, we have also discussed regarding the advantages and disadvantages of the gas turbine power plant. In this particular lecture, we will highlight some of the methods or the arrangements which can be utilized for the improvement of the thermal efficiency, or we can say to improve the performance of open cycle gas turbine plant. The three different methods which will focus as far as our subject matter is concerned. So these methods can be listed as the intercooling, then reheating and regeneration. So we'll be looking into the arrangement for all of these methods, the representation of these methods or these arrangements on the pressure volume or temperature entropy diagram. We will be also interested to write down the equation for the thermal efficiency for all these three arrangements: intercooling, reheating and regeneration as well. So let us discuss these methods one by one. Let us start with the gas turbine cycle with intercooling arrangement. Now if we see the layout for this particular cycle, so we have this LPC, then HPC, and we are having this T. So LPC is called as the low pressure compressor. HPC, that is the high pressure compressor. T, so this one is nothing but the gas turbine. Then G, so that is nothing but a generator. And here we are having a CC, so CC is nothing but the a combustion chamber, right? So the main difference that one can identify here for the gas turbine cycle with intercooling and simple gas turbine cycle. So in the simple gas turbine cycle, there was only one compressor, isn't it? So the main difference that we can highlight here for the intercooling arrangement and the simple gas turbine cycle. So here the two different compressors are used. Okay, one compressor is called as the low pressure compressor. So this compressor is nothing but the low pressure compressor, and another is nothing but the high pressure compressor. So both the compressors and the turbine and the generator, so they are mounted on a single horizontal shaft. Now why one should use for the two different compressor? It means that we are multi-staging, isn't it? This arrangement deals with the two-stage compression process. Instead of carrying out the compression of the air from initial pressure to final pressure in a single stage, isn't it? Especially when pressure ratios are very high, so that results into various difficulties, that result into various limitations when we compress in a single stage. So instead of compressing the air from initial to final pressure in a single stage, it can be compressed in multiple number of stages in more than either a two compressor or three compressor likewise. Okay, so this arrangement as such shows the two compressors, and in between two compressors we can see this mechanical element that is placed here, that is nothing but an intercooler. Okay, so intercooler is basically nothing but an heat exchanger. Okay, intercooler is nothing but an heat exchanger. So what this arrangement tells us about: a compressor utilizes the major percentage of the power developed by the gas turbine. Yes, in the discussion for the limitations or the disadvantages of the gas turbine cycle, we have seen that 66% of the power which is developed by the gas turbine, so that is used for operation of the compressor, isn't it? Two-third of the power, a big contribution, big consumption of the power is there for the operation of the compressor. So it is of interest to us that we should make an arrangement in such a way that the work which is required for the compressor that can be reduced, isn't it? So this work required for the compressor that can be reduced by compressing the air in two stages instead of compressing it from initial to final stage in a single stage, right? And in between the two compressors, we can install a heat exchanger that is known as intercooler. Okay, so we can see that the different state points, point 1, point 2, point 3, point 4, 5, and 6. So point 1 that represent the atmospheric air entering into the low pressure compressor. Then this is compressed to some intermediate pressure P2, okay, represented by the state point 2. And before the air that is getting admitted into the high pressure compressor, so heat is rejected, isn't it? This Q is nothing but the heat which is rejected by this air which is coming from the low pressure compressor, and before it get enters into the high pressure compressor, isn't it? So here we normally have an counterflow arrangement, and basically or most commonly the water is used as an coolant. Okay, so the heat exchange takes place between the high temperature air and the cold water which is circulated through the two different channels of the intercooler. So this is a counterflow arrangement, right? The air that flows from, let us say, through this lower channel from left to right, whereas the water that may enter into the channel on the upper side, it may enter from the right and it may leave at the left end of this arrangement. Okay, so this is the thing but in counterflow arrangement. Okay, we have already discussed about the different types of the heat exchangers in the earlier unit as well. Okay, so it means that the substantial work required for the compression that can be reduced by utilizing the intercooler. Okay, then rest of the cycle that remains as it is, as it was there for a simple gas turbine cycle. Okay, so this air which is cooled in the intercooler that is admitted into the high pressure compressor at condition 3 and compressed to the maximum pressure, that is nothing but the pressure 4. Okay, so this high pressure air is then getting admitted into the combustion chamber, fuel is added, fuel is burned, thermal energy of the gases that is utilized in the turbine. So these gases, high pressure, high temperature gases that expand in the turbine and develop the mechanical work, isn't it? So this is what the fundamental background or the logic behind the intercooling arrangement. So let us see how this intercooling can be represented on the pressure volume and the temperature entropy diagram. Okay, so intercooling is a process that is associated for the compression, okay, compression of the air between the low pressure compressor and high pressure compressor. So I have shown here the pressure volume diagram. Okay, point 1 that represent the inlet condition for the compressor, and if I show the compression by a dotted line, isn't it, that is nothing but the process 1 4 dash. So 1 4 dash is nothing but an isothermal compression process. Okay, so isothermal compression process which require the least work for the compression, isn't it? And then we show the process 1 to 2 and 3 to 4. Okay, 1 to 2 that is nothing but the compression of the air in low pressure compressor, and the process 3 4 is the compression of the air in the high pressure compressor, isn't it? But if this multi-staging wouldn't have been utilized, isn't it, instead of compressing in the two stages, if the compression is carried out in a single stage, then we can represent that process as 1 2 dash, isn't it? 1 2 dash would have been a process if a single stage compression would have been utilized, right? And we can see that the shaded region, that is 2 2 dash 4 3. Okay, so this particular shaded region from 2 2 dash 4 3, so this shaded region shows the saving in the work in the operation of the compressor by utilizing an intercooler between the low pressure and high pressure compressor, right? So intercooler essentially reduces the work required for the operation of the compressor. Okay, so that is what the major benefit we can get by utilizing the intercooling arrangement. Now, if I look into the temperature entropy diagram, okay, the process 1 to 2. So 1 to 2 that represent the asentropic compression of air in the low pressure compressor. Then process 2 3. So process 2 3 represents the cooling of the air in intercooler. Okay, temperature of the air is reduced from condition 2 to condition 3. And I can see that the process 2 3 is nothing but a constant pressure heat rejection, isn't it? So cooling of the air in the intercooler is an isobaric process, constant pressure process. I would like to also draw your attention that the temperature T1 and temperature T3, okay, the temperature T1 is nothing but the temperature of the air entering the low pressure compressor, and temperature at point 3 T3, it is nothing but the temperature of the air after the intercooler or before it enters the second stage compression, high pressure compressor. So if both these temperatures are same, that is T1 equal to T3, okay, which is shown here by a dotted line, T1 equal to T3. So such intercooling process is known as a perfect intercooling, right? Such process in which the temperature of the air after intercooling is brought to the initial temperature, then we call such intercooling process as a perfect intercooling process. And if it is not that like that one, it means that the temperature T3 is slightly higher than that of the temperature T1, then it is called as the imperfect intercooling. Okay. Condition 3 that represent the state of the air that enters into the high pressure compressor. So process 3-4 is the compression, asentropic compression of the air in high pressure compressor. Then the process 4-5. So 4-5 on the temperature entropy diagram, that is a heat addition at constant pressure in the combustion chamber. Okay, resulting in the rise in temperature from T4 to T5. And I can also observe that the maximum temperature in the cycle, so that occurs at 0.5. Okay, after the heat addition, the temperature will reach to the maximum value, that is the temperature at 0.5 T5, or in other words, the T5 is nothing but the temperature of the gases which is entering the gas turbine. Okay, Tmax, that is equal to T5. So process 4 to 5 is nothing but the constant pressure heat addition in the combustion chamber. And then the process 5-6, asentropic expansion of gases in the turbine, developing the mechanical work. And lastly, the process 6-1, so it is isobaric heat rejection from these gases to the surrounding. It means that the gases are exhausted into the atmosphere. Okay, so that way the temperature entropy diagram can be elaborated for arrangement utilizing the intercooling between the low pressure and high pressure compressor. If I want to express the equation for the thermal efficiency of the cycle with intercooling arrangement, okay, so the numerator essentially is nothing but the net work from the cycle, and denominator is nothing but the heat input, or that is nothing but the heat supplied at constant pressure process. Okay, so numerator, if we see the H5 minus H6, okay, H5 minus H6, so 5-6 is nothing but the expansion process, isn't it? So that is nothing but the work which is done from the turbine, isn't it? So H5 minus H6 is nothing but the turbine work. Okay, turbine work minus the compressor work. So compressor work is nothing but this H4 minus H3, H4 minus H3, that is nothing but the work for the high pressure compressor, and this H2 minus H1, so that is nothing but the work which is required for the low pressure compressor, isn't it? So the turbine work minus the work required for the low pressure compressor, work required for the high pressure compressor. So if this is taken into consideration, that is nothing but the net work so which is nothing but the numerator here as such, and denominator, that is nothing but the input, which is nothing but the heat supplied in the combustion chamber. So we are quite aware that the heat is supplied during the process 4 to 5, isn't it? So difference of enthalpy H5 minus H4, so that is nothing but the heat which is supplied during the constant pressure process. So that way the equation for the efficiency of the cycle by utilizing the intercooling arrangement can be expressed, it can be written in this fashion. Okay, the another arrangement for improvement of the performance for the gas turbine cycle, so that is nothing but the reheating. We'll discuss this particular arrangement in the upcoming session. So thank you very much.